Okay, welcome back to the course of Introduction to Algorithms. My name is Azamat Ordabekov, and this is a video of week 2 lecture. Today's topic is arrays, linked lists, and hash tables. So today's plan is that I will talk about arrays, linked lists, and hash tables. I will talk about their advantages and disadvantages in terms of the asymptotic analysis. And lastly, I'll talk about the problems which can be solved by using these data structures. Okay, let's get started. So first is the array. Array is one of the simplest data structure. I guess many of you are already familiar and you used array many times. And but anyways, let me define the definition of array. Array is a data structure consisting of a collection of elements, each identified by at least one array index or k. So here you see the time complexity of array. As you can see, uh, access takes constant time. So it means that if you have the index of elements, you can at constant time get that. And the search takes linear time complexity because we have array, and in order to find some elements, we need to go through all the possible elements, and search takes linear time. Insertion and deletion also takes linear time complexity because if you remember from the lecture of week 1, I explained you the amortized analysis, and as example of amortized analysis, I provided you how I explained you how dynamic array adds and elements. So whenever we have new element and there is no empty space, uh, the compiler needs to reserve a place in the memory with the double size of previous old array. So and copying from the old place to the new place takes constant time complexity, and that's why the insertion and deletion takes linear time complexity. In terms of deletion here, why it's linear? Because when you remove one element from the array, let's say you want to remove one element in the middle, uh, you take it out, and you need to shift all the elements after that to the left. And in the worst case, it takes linear time complexity. Linked list. Um, the next data structure is linked list. A linked list is a data structure that represents a sequence of nodes. There are two types of linked lists. First one is a simply linked list. So in a single linked list, each node points to the next node in the linked list. And in a double linked list, each node points to the next node and to the previous node. So linked list at least holds two information at the same time: the data itself and to the pointer to the next node if it is a single linked list. If it is a doubly, it holds three information. One is the data itself, second is a pointer to the previous node, and the third is a pointer to the next node. And here is asymptotic analysis of linked list. Access takes of n time complexity because unlike array, in a linked list there is no indexes, and usually you have only access to the beginning of the linked list, and in order to get to some node you need to go through all those elements until you get that element. In a search, it takes also linear time complexity because you need to go through all the elements, and there is no efficient algorithm that runs faster than linear in order to find some element in linked list. Insertion and deletion takes constant time. So this is the advantage of linked list comparing with array, that insertion and deletion takes constant time complexity. Um, when I talk the insertion deletion, I'm talking about uh, the function that only inserts or deletes. So if you want to add element, you just take it, put to the place, and change the information of the previous node and the next node. The same applies for the deletion. So if we go back, the advantage of the array is that it has constant time access time complexity, and but the disadvantage is that it takes linear time complexity of insertion and deletion. In a linked list, uh, the advantage is that it takes constant time in terms of insertion and deletion. So if you have a lot of operations where you need to add or delete elements, it's better to use linked list. And here is a diagram of single linked list. So as I said before, singly linked list holds two information. One is the data itself, and second is a pointer to the next element. So here we store the address of the next element, and here we can, from this part, we can define what is the next element. So this is the head of the linked list. We start with the head, then go to the next, to the B, then to the C, and to the D. And the last element, next pointer to the next element, shows to the null. It means that we don't have any elements after the D. And here is a double linked list. In a double linked list, again, as I said, that we store the three information. One is a pointer to the previous, one is the data itself, and the third is a pointer to the next element. And here is a diagram of double linked list. In part A, we have a linked list where the head is a 9, and as you can see, the head point node, it doesn't have any information of to the previous node, and it shows null. And for the next pointer, for the last element of the linked list, the next pointer shows also null because there is no elements after that. And on part B, we see how do we add elements to the double linked list. So initially we had this linked list where the head was a 9, then we had 16, then 4, then 1. And on the part B, we decided to add new element with the K25, and we just changed information on a node 9. We say that previous points to this one, and the new element's next pointer is points to the 9. And for the previous, we say it's a null, and we head is the 25. And on part C, here is example how does the deletion work. Here we say that we want to delete 4. Initially 4 was between 16 and 1, and when we decide to delete, we just take it out from our linked list, and we just change the information on the node of 16 and on the node of 1, where on the 16 we change next pointer, and at 1 we change the pointer of 1 of previous pointer. Here is almost at all modern languages you have already built-in arrays, but linked lists, in many languages you need to create the customized structure to create the linked list. Here is an example of linked list in C++. You create the struct. Struct is kind of class, and you define the next properties like value and pointer to the next element. And if you want to do through here is example in Java. It is also something similar. You create the property with next, and the data itself. And if you have any other languages, please take a look, um, take a do a search on how to create linked lists on your language that you are comfortable with. And here is the example of searching at linked list. So as you can see, let's say that we have linked linked list L, and we want to find the node K with data of K. And initially we say that X equal to the head of the linked list, and we create the while loop saying that it will run until our current node is not equal to the K. If it is equal, uh, our while loop breaks and we just return the X node when we found it. And from that, of course, you can assume that the search takes linear time complexity because it needs to check every element, compare it, and if it is equal to our target element, after that it breaks, or it reaches the end where like x is equal to the null. So here is an example of inserting element into the linked list of code. So we have linked list L, and um, we want to add x. So we add x to the beginning of our linked list, and we say that x next is equal to the head of our linked list. And this part of the pseudocode checks if our head is not null, so if our linked list exists or not. And from that, you can see that the insertion takes constant time complexity because there is no while loops, there is no recursion, and because of that, there is whatever the size of linked list, it takes always constant time complexity. And here is an example of deleting. Um, Here in deleting, we just check, we just change the values of the previous node and the next node. We have linked list L, and we want to delete node X. So we just change the values of previous node's next pointer and next pointer's previous next node's previous pointer. And the deletion takes constant time complexity. Of course, here, why I'm talking about constant, I'm not including the searching element. Here I'm pretending that already um, I have already found the deleted the element that we want to delete, and just the pure deletion itself takes constant time complexity. So here is a pseudocode only of deletion of itself, pretending that we have already found our element. And next data structure, which is very powerful in terms of the lookups, in terms of the finding element, is a hash table. Hash table is a data structure that maps keys to values for highly efficient lookup. So here is the time complexity. The access takes linear time complexity, search also takes linear time complexity, insertion takes constant, deletion takes constant time complexity. Usually, if you have many operations where you need to search for some target elements, it's better to use hash table. But you may assume that why we need to use hash table if we want to find some element, and the searching takes linear time complexity. Actually, the searching takes constant time complexity, but because of some collisions that may happen, the searching takes linear time complexity as well as access. But on average, The amortized time complexity is constant both for the access and for the search. So on average, every element, every operation on a hash table takes constant time complexity. So it's a very powerful tool um, for the many cases. And here is an example, one way of creating of using of creating the hash table is direct address tables. So what is a direct address tables? It means that um, when you want to find some elements, you have already predefined the index of that element, and the index or k of that element is between some kind of range of elements, like assuming that it's between 0 and m minus 1. So let's say that we want to store some element, keep it somewhere, and the element itself or the key itself is a way how to where to store it. So we have, uh, let's say that we have some array, and on that array, according to the index, we can find our elements, or we can store. So here, example of how do we do search. So T is some data structure where we store our data, and K is the element that we want to find. So, and in order to find that element, we just return the K's position at data structure of T. And insertion here also takes time, constant time complexity, because we just assign to a data structure T at position xk the value x. And for the deletion, it also we just change the value to the nil, and that's it. And each of these operations takes constant time complexity. But of course, this is not a good approach to use hash table. It's very similar to array. That's why it has some limitations that I will talk on the next slide. But here is a diagram of direct address tables. So let's say that we have universe of case, and we have some like case, and according to that case, we can define where we store our element. And T is kind of very similar to the array. So here on this slot, we store two information, like the K itself and the satellite data that we want to store. But direct address tables, as I said before, it's had some limits. And the first one is the case should be predefined. So um, the key, for example, if you have data structure T with size 100, um, you should have the case like between the 0 and 99, or between 1 and 100, including. And usually it's not practical, it's not convenient. Um, and, um, and the next limit is that it works for small number of cases again, because usually we don't know how many cases do we have. But if you want to use direct address table, you need to predefine how many cases are you gonna use, and it also puts some limits on the usage of this data structure. And of course, third one is the possibility of wasting memory. It means that, for example, before you may assume that you're gonna use 100 case, and but on a practice maybe you just needed only 10 or 20, and the 80 would just be stored on a memory waiting for its own case. But it's totally possible that you will have many slots which not gonna be used. So direct address table is not very convenient. That's why we have hashing. Hashing means that use some hash function which converts the data or the key. So after that, we can define where our data is located. So it all depends on a hash function. So let's say that we have uh, k with variable with letter k, and after the hash function, we define where our data is located. And here is a diagram example of hashing. So as you can see, let's assume that we have some universe of keys, and unlike from the previous hashing methods, uh, we don't need to define predefined keys. We can take whatever key we want to use and do some hashing, and after that hashing, we can define where our data is located. And also, we don't need to define the size of the T, so we don't have something like wasting of the memory. And here is the methods of for hash function. Of course, hash function is very important in converting the data itself. And we have mainly two ways for the hash function. First one is a division method, and second one is multiplication method. So first is a division method. Division method means that let's say that we have k, and we want to store this k in one of the m slots. So we take the remainder of k divide by m. So we have hash function as like this. So we take mod of m. So let's say that we have m equal to 12 and the k is equal to the 100, and we take the remainder of k divided by m, and it's after that operation we have 4, and the 4 means that at slot 4 we will store our data. And you need to also pay attention on m. You need to choose m very carefully, so you would have on each slot unique data. So it depends a lot from the m. So please pay attention on them choosing m. And next method is the multiplication method. The multiplication method is a little bit complex comparing with the division method. In the multiplication method, we create function that operates in two steps. First, we multiply the k by constant a, which is in a range of 0 and 1, and we need to extract the fractional part of ka. Then we multiply this value by m and take the floor of the results. So in the short, we would have this hash function. But there can be, of course, you may assume that the hash table is very convenient in terms of the accessing, in terms of searching, in terms of the deleting or inserting the elements. But there is one big problem that can happen, is that it could have the collision. Collision means that on a hash table, two or more different keys have the same hash code, and that's why on one slot we need to store many different data. So if we let's go back to the division method. If we have m equal to 12 and k, let's assume that also something different, we there is also high probability that we can get the 4 after the hashing. And if we get again 4, it means that two different data they can refer to the same place. But we can avoid the collision with 4 main methods. First one is we chain with a linked list, then we use array, then we chain with a binary search tree, and the last one is open addressing linear probing. So what is chaining with a linked list? It means that um, on a place, on a slot, we store the pointer where our linked list is located. So here is the example. Let's say that we have two strings and we need to keep both of them. It's high and ABC. After and let's say that we have k the k of high is this one, and after the hashing it shows to the slot 0. So we put high on this place, and then we have string ABC that has a k this value, and after the hashing it also shows this slot. So in order to keep, we need to keep both of them. We cannot remove or throw away one of them. We need to do something. So we just on slot 0 we do something like pointer to a place where we have the linked list, and in the linked list we chain this both information, so we could store both of them. Of course, if we have the collision something like this, um, the time complexity of the searching and accessing take change to the linear time of how many elements we have at the slot 0. And why, you may ask, why do we need the linked list in a chaining? Because as I said before, in a linked list the adding and the deleting the element takes constant time complexity. So whenever we have new data which also refers to the same slot, but that slot is been reserved before, we just on a constant time add the ABC to this slot. And also, of course, we can use array here instead of linked list. But if you remember, the insertion and deletion of element in array takes linear time complexity. And also we can chain with a binary search tree. It's also data structure. Um, but I will talk about the binary search tree on the following weeks. But for the binary search tree, we need to have something like ordered data, or the better is to use some integers, because a binary search tree is very convenient when we have ordered data. And the last method is open addressing linear probing. So what does it mean? In open addressing linear probing, we don't use any additional data structure. In all previous methods, we used linked list or array or binary search tree. In open addressing linear probing, we don't use any other additional data structures. So what does it do? So we choose some integer. Let's say that it's 5, and again, let's say that we have string high. It has k something like this, and after the hashing, it shows to the 0. And we put high into the slot of 0. Then we have next integer ABC. It has ID of the k of this, and after the hashing, it also shows to 0. But we move +5 position after this collided slot and put it somewhere here. So let's say on index 5, and we store ABC here on slot number 5. And again, let's on the next step assume that we have string AA, and it has k this one, and assumes that it doesn't, after the hashing, it doesn't point to the 2 but to the 0. So what does it do? We again go to the 0, we see that 0 is already reserved, then we jump 5 positions, and on 5 we again see that 5 is already again reserved too. So what do? We again jump to the 5 positions, and so we, let's say that we store, and we see, go to the slot number 10. On the 10 we see that 10 is not reserved, and we store AA on slot 10, and we do all of that to all other positions, uh, all other data, till we find our uh, free slot. Of course, you need to pay attention on choosing the integer for which we will jump whenever we have some reserve spot. And basically, you need to choose the number based on how many elements are you predicting to have. So maybe some case in on some cases you may know that you don't need more than the 10 elements, but you may assume that you can have the collision, and you can choose instead of 5, 10. So whenever you have reserved space, you jump to the 10 positions. And here um, collision resolution by the chaining. Here is example. How do we do if we use linked list in order to avoid the collision? So here we use insert. Insert means that we add to the head of the elements. Search, in a search you need to go through all the elements in your linked list, and on a deletion, the deletion itself takes the time, constant time complexity. Of course, here is asymptotic analysis. As you can see, insertion and deletion takes constant time if it is a double linked list, but for the single linked list we have also the same asymptotic running time, but the implementation a little bit complex because you need to change the values of the previous element, go back to that and change it. And of course, almost at almost on at all modern languages, programming languages, hash table has been already implemented. Unlike linked list, where you need to create the class or structure in hash table, the hash table has been already implemented. So, and usually you have the hash set or hash map. And in Java, as far as I remember, you just set the hash set or hash map. In Python, you define the dictionary. In C++, you have unordered set and unordered map. So what is a hash set? Hash set uh, is a set where you just store only one, where you need to only one data. So according to that data, you do some hashing, and after that you define where your data is located. And on the hash map, you need a key to define where your value has been stored. So let's say that you have value 2, the string 2, and the key far. In order to find the 2, you need to hash this value far, and after that you can find your value. So in a hash set, you need only one data. In hash map, you need to, in order to find some value or some element, you need to use k. So next part of our lecture is the problems. So first I will show you some problems, and the best way to solve the problems is to first analyze the problem, try to solve on yourself, uh, and after that check your solution with mine. And of course you may watch this lecture. You can make a pause, think how to solve that problem, um, think about the many possible cases, and after that you can press play or continue and compare your solution with mine, with the problem or with the solution on the lecture. So first problem is called is unique. So you need to implement an algorithm to determine if a string has all unique characters. So here's the example. We have input ABA. It should output false because the letters in this string are not unique because we have AA twice. So that's why it's false. But here in this string, we have a lask and each letter is unique. It's never been repeated before and it should output the true. So before jumping into the solution, press pause, think how you would solve this problem. And after that, if you have some solution problems, you can press play, continue, and compare your solution with mine. So here is the solution to the problem. So here we just use hash table. If you remember on a hash table, we just the time complexity of finding some element takes constant time. That's why we need to use hash table. Here is a solution in C++. We create the hash table, hash set. So in C++, again, the hash set is unordered set. Then we go through the string, and for the each character in the string, we check do we have that element in set or not. If yes, if we don't have that element, we insert that element to our set. But if we have already seen that element before, we just return false. And after checking all the elements, we just return true. And the time complexity and space complexity. So we need to analyze how much time the solution would take and how much memory it would take. How much additional memory it would take. I would pay attention on that. So the time complexity is O of n. N is the length of the string. So how many characters do we have in S? Then space complexity also takes O of n. But why? Because we need to use additional data structure, and on a worst case, each element, each character can be unique, and we need to store all the elements. That's why the time complexity is O of n. And if we put one more um, restriction, saying that if we cannot use additional memory, how can we solve that problem? We could solve this problem by sorting the string, and as you know, in a string, each character in ASCII code has some value. So A, for example, the value of A is lower than the value of C. And in ASCII code, the value is based on the alphabet. So if we apply the sorting, um, all the same elements, all the same characters would stay next to each other. And if, for example, initially we had example A, B, A, A, and if we do sorting, we would have A, A, B. So after the sorting, we would just compare these two neighboring elements. And if they are equal, it means that we don't have unique characters in the string. In that case, the time complexity would be, because of the sorting, it would take n log n, because there is no better sorting algorithm that runs faster than this time complexity. And the comparing elements, second part of our solution would take O of n time complexity. Sorry for my writings if something not clear. Okay, next problem is check permutation. So we have two strings and we need to write a method to decide if one is a permutation of other. So here we have two strings ABA and second is also AAB, and we need to define as these two strings permutation. What does mean permutation? Permutation means that they consist of same number of letters and the same letters. So because both of them consist of two A's and one B, this is a true. This is a false because this string has two S, but here we have only one S. That's why it's false. So before jumping into the solution, press play, think how would you solve this problem, and after that press continue or resume. So here the first solution is to again sort the strings, both of the strings, and compare them. So here example, we sort first word and second word, and we compare after sorting both of them, and we would, if the letters are not equal, then return false. The time complexity again consists of two parts. First part is sorting, and second part is comparing these elements. And sorting takes again n log n, and comparing takes linear time complexity. So here is and space complexity, because we don't use any additional data structure, any additional variables, uh, it takes as constant time complexity. And next, of course, is to second way to solve this problem is to use hash map, where k is a character itself, and the value is a number of how many times have we met that element. And so we go through each string, add that character of each string, and count how many times do we have that character in a string. And after adding all the counting of all the characters from the string, we compare the values of each k, and if something not equal, we say that it's false. But if everything is equal, then we return true. And the time complexity also, it consists of two parts. First part is counting the characters, and the second is comparing them. Each of them takes linear time complexity. So the time complexity is O of n for this problem. And space complexity, because we use two additional data structures like hash map, we need to create two hash map for each string. It also takes O of n time complexity. And next problem is so we have array of integers, and you need to return the index of two numbers such that they add up to the specific target. So here we have in array of something like this 2, 7, 11, 15, and the target is 9. Even though that the example is sorted, initially we assume that our input data is not sorted. So here output is indices that sum up to the target 9. So if we add 2 and 7, we have 9, and the index of that is 0 and 1. So first solution is to use brute force. So what is a brute force? Brute force means that we try um, every possible way to solve that problem. So we take every element and add up with all other elements, and we see that if that equal to the target or not. And because we take every possible case, we take every possible element, add up with all other possible elements, it takes a lot of time complexity. It's O of n square. Why O of n square? Because um, we take each element and compare with all other elements. And we have here, as you can see from the code, we have two for loops. And second solution also is to use hashmap. And in hashmap, we store the difference between the target values and all other elements between the target and the element itself. And because we use hashmap, it saves us the time, but we have more the space complexity because we need to use additional data structure. And so here is the time complex O of n and space also O of n. And from the code you can see we have only one for loop, and that's why it's O of n. Next problem is deleting middle node. So this question is related to the linked list. So you need to implement algorithm which delete a node in the middle of single linked list given only access to that node. So let's say that we have A, B, C, D, E, F. It's single linked list, and we need to remove the middle. So remove the middle is the C. O is the D. But let's assume that we need to remove C. So what do we do here? So I want to remind you that in a single linked list, if we have elements like access to the C, we cannot move back. We don't know what other nodes were before us. We only know which elements after this our current node. That's why it's makes the problem more challenging. So what do? We count number of nodes. We go through all the elements from the heading, count how many elements do you have, and if we have 6 elements, it means that we need to remove third element. And first we iterate through all the elements and the number of nodes, and on the second we already know what is the size of linked list. We need to iterate again, and when we reach let's say third node, we need to change the value of 2 and take it away the third element. Or we can use the runner technique. So what does it mean, runner technique? In a runner technique, we have 2 pointers, both of them starting from the head of the linked list, and one pointer goes twice as fast as a second pointer. So here we have slow pointer and fast pointer. Fast pointer moves as at the speed of twice of the slow element. So why you may assume that this technique would solve the problem? Let's assume that we have 40 kilometers of roads, and let's say that we have two cars, and one car drives at the speed of 20 kilometers per hour, and second one drives at the speed of 40 kilometers per hour. And of course, in 1 hour, the car that drives at the speed of 40 kilometers per hour, it will reach the end of the road. Meanwhile, the second car, which has the speed of 20 km per hour, will reach the middle because it has the speed um, slower as twice slower than the faster car. That's why when the fast will reach the end of our linked list, slow will stay at the middle. And here we just change the next pointer and solve that problem. Here the time complexity is much better because we have only one while loop and it will run only once, and the time complexity is linear of 1 of n, and space the constant. Even though that we use additional pointers, whenever the size, the length of the node, we always use 2 pointers. That's why the space complexity is constant. Next problem is loop detection. So we have a linked list. We need to determine if it has a cycle in it or not. So what do we do here? We start with the 3. Again, in a linked list, it is possible that we have cycle where the node of -4 points to the some node that has been before. To the in this example is the 2. So again, in the linked list, we have access to the head of the linked list, and we need to determine does it have a cycle or not. So what do we do here? We can use hash set. We can add the nodes into the hash set and check every time have we seen that node on seen or not. And the time complexity takes O of n because the n is the length of our linked list, and the space complexity also O of n. And next, we can use again the runner technique. Same applies. The same technique applies for this problem also, where we have 2 pointers. One is a slow, second pointer is a fast, and fast also runs as twice faster than the slow. And if we have 2 pointers with different speeds, at some point they will meet at some node. But if fast will reach the end of the linked list, so it means that it reaches some node where it shows null. It means that we don't have cycle on them on the linked list. And the time complexity is O of n, and the space, again, because we have the constant amount of the pointers, it takes O of 1. And for this week's reading is, by the way, this was the last problem, and the readings for this week is this chapters 10-11 from the Introduction to Algorithm by Korman, Lacerson, Rivest, and Stein. For the following weeks, I will call this book shortly as a CLRS. So whenever I say CLRS, I assume this book. Okay, so please read these chapters and be prepared. So here is the summary. Very shortly, today we covered 3 data structures. We compared them. I explained what is advantages and disadvantages. In array, you have fast access if you know the index. In a linked list, the advantage is insertion and deletion. It's because it's a constant time complexity. And hash table is better to use when you have fast lookup, like fast when you need to find some element in a very short period of time. And please also you need to consider the ways for the hashing and avoiding the collision. So guys, that's it. Thank you for the watching. Bye.